Why is reconciling inflation theory with quantum gravity difficult? Imagine trying to fit two puzzle pieces together that are made from completely different materials. That's similar to what scientists face when they try to combine inflation theory with quantum gravity. Inflation theory explains how the universe expanded incredibly fast just after the Big Bang, driven by a mysterious field called the inflaton. This process happened at energy levels close to the Planck scale, which is the smallest measurement of length and the highest energy where quantum effects of gravity become important. Quantum gravity, on the other hand, aims to unify Einstein's theory of general relativity, which describes gravity on large scales, with quantum mechanics, which rules the tiny particles and forces. The problem is that these two frameworks work on different rules and scales. Inflation models often treat spacetime as a smooth, classical fabric, while quantum gravity insists that spacetime itself is made up of tiny, fluctuating quantum bits. This makes it hard to create a single picture that explains both. One big challenge is figuring out the initial conditions for inflation. It begins just after the Planck time, a moment so close to the Big Bang that quantum gravitational effects are dominant. But current models don't tell us how to set these initial conditions in a way that fits with quantum gravity. Without that, we can't be sure how inflation could start at such a high energy level. Then there's the issue of fluctuations. Inflation predicts tiny ripples in the universe that grew into galaxies and clusters. These fluctuations need to be described as quantum phenomena, but existing inflation models don't fully explain how to do this within a quantum gravity framework. Another complication is the universe's large-scale uniformity, which inflation was supposed to solve through rapid expansion. But reconciling this with quantum gravity requires a new way to understand how spacetime behaves at the smallest scales and how it influences the large-scale structure. Plus, scientists are still searching for direct evidence of inflation, like the gravitational waves it should produce. These waves would leave patterns in the cosmic microwave background, but so far, clear signals have not been detected. This makes it harder to confirm whether inflation really fits with quantum gravity. Finally, many inflation models depend on hypothetical elements like the inflaton field and its potential energy, which are not yet grounded in a complete quantum gravity theory. Different models suggest different ways the universe might have behaved, leading to many competing ideas. This scientific puzzle requires long-term research, advanced technology, and collaboration across fields like cosmology, particle physics, and quantum theory. In the end, uniting inflation theory with quantum gravity is about bridging the gap between the very big and the very small, a task that remains one of the most exciting challenges in understanding our universe.